Okay, so this is the next phase of the demo. I was initially just going to do all this in one video, but it was taking too long. You may have seen in the prior demo, I did a mode solve of a strip waveguide. Now I'm going to go ahead and use that mode solve and launch a mode with FTTD and go around a bend. And so uh, right now the network on this computer is seriously wonky, so there may be some warnings and stuff here. Before you criticize my software too much, I would say right now email and web browsing is not working. So this is working for now. So that's something. Anyway, let's just see how things go. I'm going to create a new project and call it Bend. And this is going to be, let's make it a 7 micron bend. That should be fairly minimal loss. We'll not use an Euler bend, just a cylindrical bend. So create mesh domain, and this is much the same as what I did for the mode solve. Okay. All right. So create view2D. All right. So the first thing is, let me just copy this box structure over. Actually, I'm going to create a little group in here called structural group. Oops. Yeah, I didn't make that the insertion point, so cut, paste, Control X, Control V. There we are. Now it's in here. So this is the same exact cross section as we did the mode solve. Now this is the XZ plane for Z, or XY plane for Z equals 0. But actually, this is a full 3D CAD system, so there's also the top view, we call it. And we're going to have the view direction be negative Y. I would recommend negative Y instead of positive Y. I think it does work with positive Y, but the axes get confusing sometimes. So, but use positive X or positive Z. And now we're looking from above. This is an isometric drawing of the waveguide in the third dimension. So, let's have the waveguide mode launched at around 1 micron, and the bend will start at around 2 micron. So to that end, I'm going to just draw this out. And my simulation will start at Z equals 0. You could start it anywhere. I'll just start it at Z equals 0. That means there'll be a boundary condition right here. So we'll want to not launch the mode right at the boundary condition, because you don't want to do that. All right. Simulation domain. And this time we'll do FTTD. Now you may note there's also a frequency domain solver. That is not quite ready just yet. That is something that we're still working on, but FTTD should be ready for prime time. So let's see. I think this is probably big enough. Let's look at what that looks like from the top. This is my FTTD simulation, and yeah, we might want to adjust this, but let's create the bend first. So yeah, cylinder. So we'll just start by drawing this in here. And probably the easiest thing is just to set everything by just manually. So we know we want the center of the cylinder to be at 2 in Z. We'll worry about X in just a little bit. In Y, remember the waveguide starts at 1.5 microns, so we'll make it start at 1.5 micron in Y. The Z axis for the cylinder, which is the forward direction, we'll make that positive Y. X axis can be 1, so 1, 0, 0. So Z is 0, 1, 0. This is the local coordinate. Length is the length of the waveguide, so 0.2. So that actually looks about right. Now we'll want a 90-degree bend, and we'll want it to have the appropriate inner and outer radius. Inner radius, 6.75. Outer radius, 7.25. And we will, yes, use inner radius, yes, use partial theta. And yeah, it looks about right. The one thing is we should do this. All right, and now two more. Okay. Now, you may note this is a little bit jagged. That is just as it's being rendered in the rendering window. You could make the wire resolution a bit larger, and then it would look finer. But there's no need, because when the structure is actually rendered for the simulation, it's done analytically. So it will be exactly right to machine precision. It doesn't use this bend. That's the nice thing about using cylinders. It's a precise thing. We can see that the FTTD simulation is not quite large enough, so let's just make that a bit larger. All right. So now we need to have a similar waveguide over here that then will be the output for this. So actually, the easiest way to do this is copy paste. Now we're going to rotate this thing, and to this end, transform window, rotate. And here we can use the Euler angles, and it's not exactly intuitive, what the angle might be, but luckily there's an easy way. It's just I happen to remember from a previous simulation that this is what I need, but these are in degrees, of course. You can see where the different axes are mapped to. X-axis will be mapped to -z, which is reasonable. Y will be maintained, and Z will be mapped to +x. So let's see what happens. So, yep, okay, it's the right orientation, the right Y location. However, it needs to be dragged a bit to get to the right spot. So we'll just translate it. I'm going to hold down Control, so I only drag by integral values, and then hot point. Okay. So actually, the bend is starting to take form. In fact, it's pretty much done. I'm going to save this. There is the mode solve file from the previous thing. Let's just take a quick check. How big is this FTT domain in terms of memory? Scan domain. 1.7 gigabytes. That's quite small, actually, and easily accommodated by the GPU that we have, which has, I think, is 24 gigabytes. We'll just quickly set up the boundary conditions. The plus X axis, we'll just make that PML. There we go. And oh, you know what? Now might be a good time to set the material property. They're all going to be a silicon, so we'll just set that now. If you try to run this and you didn't specify that, it will flag an error of some sort. So we're going to now need to launch and measure this mode solve. And to do that, we need an object that will sort of grab on to this mode and present it in a way that the simulation framework can use. And there's several different ways of doing that. The best thing is what I call the field slice object. And this is described in much more detail in the manual. There's a number of examples using this. So the field slice object, we have to specify, there's several different things it can do. It can also be used to capture fields from a simulation and then relaunch that. And so it's a little bit confusing sometimes as to how to use it. But, so we're going to mode specification, mode solve, and then I specified the mode solve object by saying this to be operand 0 and then right-clicking, which is most of what we need to do. What else do we need? You can choose to use a single mode at the central frequency, or you can choose to use a range of modes where it just downloads all the modes across the frequency. We'll just use a single mode for now, and that'll be fine. So download, everything works. I'm just going to save this project, which is the mode solve project. And okay, so let's see what I need to do here. Okay, Now I need to create a mode launch object, and the way I can do that. Oh, there's one actual thing I forgot to mention. So what I like to do is to shrink the compute domain by maybe 2.2 micron. This just carves off some of the zero field at the edge. You can see that it made the field size a bit smaller. Don't have to do that, but then I would need to expand this domain to be just a little bit bigger because you don't want the field size to touch the boundary condition. Okay, so field launch, mode launch, and the insertion point is set to FTTD. Okay, and here I'm going to show something that is, I think, a little bit useful. I'm just going to draw this approximately where I want it with the orientation that I want it. The orientation being the z-axis, which is where the direction the mode will be sent in. I want to launch the mode in the plus C direction. So you can see that that's indeed what we have. Now there's a problem. It was created right at its equals 0, but we can fix that easily. Let's just move this to 1. Okay, so there's the mode launch object. It's not quite the right size. It's not quite the right location. How can we fix that? Well, easily. So we're going to, I set the solve mode object to this field slice, and now I am going to, when I hit download, you'll see it actually detects what is the best location. Oh, what's the best location to match this mode solve? Something has gone wrong because the structure is not matching. What happened? I think, oh yeah, I did not set the background material for this simulation domain. So let's set that. Yeah, one of the reasons I like this feature is then if you didn't match, oh, perfect. Okay, now we have a perfect match. And so it made, yeah, it matched the geometry perfectly now. If it's close, like there's one grid point off, it'll tell you, but it'll still get a best fit, and that's probably usable in most circumstances. So now we'll also need to do a measurement, and I want to do a mode measure. Mode measure is fine for our purposes. I'm going to create this, and I'm going to measure it at 1.5 in the z-axis, and you can see. And the mode measure is actually very similar to mode launch. The one thing is we're also going to want to specify the frequencies at which to measure, because we're going to launch a pulse, you see. And actually, while I'm on that topic, let's make the pulse. I'm going to make it about 55 femtoseconds. So you can, play with the pulse information here. Let's see here. For the mode measure object, we're going to want to do a couple things. First, we'll specify the frequencies to measure that we want to measure this bend loss at. Okay, 5 frequencies, 15, 20, 15, 30, 40, 15, 50, 15, 60. And this pulse is fairly broad, so it certainly will have enough power in these different frequencies to get meaningful data. And the mode shape has not really changed. If we were really concerned about the mode shape changing, we could have, like I said before, set that field size to have multiple modes that it downloads. So this is actually almost ready, but what we do need to do is specify the frequency group. And so here, and the reason to have this is that then you're guaranteed that all the objects using that frequency group are in fact measuring the same frequencies. So solve mode object is this thing. There we go. There we go. Now download. Great. It did it again. So again, it matched the mode perfectly. And it had adjusted its size and everything that may have been hard to see to match exactly what we were expecting. Now we just need to create a mode measurement surface over here, and we'll almost be ready. I can do that by copying and pasting this, I think. So there we go. Let's just do this little rotation thing again. Yeah, rotate. All right. But now we need to drag this thing a bit. Actually, it's hard to drag it because it's sort of this 1D thing. Maybe I can do it. Let me see if I can do it. No, I think I can't. But so we'll just manually set the location to be x equals 11 and z about 9. And we only have to get close, right? Because it's going to automatically detect. Okay. And so I found a perfect match. Now, one thing to look out for a little bit is what is the x-axis? The x-axis should be in the direction of t0. Here it is positive 1 in the z-axis. And yeah, that makes sense because that's, that should be fine. If this were in the y direction, something went wrong in my rotations or whatever. And you can see that vertically it looks to be the same as this. Okay, I'm going to save everything. We are just about ready to run the FTTD simulation. Oh, there's one more thing. We need to render this thing, and I'll just do it in the top view, but you can render as many things as you like so that we can actually see what's happening. Wait, what happened? Oh, I didn't actually do anything. Oh, there we go. Okay. And I'll start by rendering EX, which is the default, but then I'll change it to HY because that's a better thing to render because that's going to be, EX is, as you rotate around here, is going to not be the dominant field anymore. So it's not a great thing to be looking at. And what else should I do? Well, I already talked a bit about setting up a local cluster. So let's just specify that. And you really want GPU selected for FTTD. It's so much faster. And a good number, by the way, is like 200, 300 gigaflops per second. We'll see if we get that. All right, we should be good to go. So let's see, did I forget? Oh, I think I did forget one thing. So the render plane, I made it at y equals 0. And all the action is at y equals basically 1.6. So yeah, I'll just change that. Save. And yeah. Start FTTD. Sometimes I've noticed if you have a really complicated structure, this part will time out or something. It shouldn't usually happen. If it does, you may want to adjust this thing, default timeout. It'll tell you what the timeout was that expired, which will help you track down which of these various settings is the issue. And oh, now we have to select how long do we want the thing to run for, so target time. I'm going to say 300 femtoseconds, and if that wasn't long enough or too long, it doesn't matter. It just, we can set that later. And then start time step. All right. Okay, 109 gigaflops per second. That's not crazy fast. But this was kind of a smallish domain. This is not terrible for a GPU. For larger domains, hopefully it would be larger. If you use a cloud machine, sort of a DGX A100 box, you can get well past 1,000 gigaflops per second, maybe even 2,000 if you're using an 8X H100. Please note that if you have multiple GPUs in your machine, they will all be used. And any second now, we should see the field in this window. I actually don't know why it's not doing that. Oh, I see why. The field, the render object needs to descend from the FTTD object. So I just changed the insertion to FTTD and copy pasted. And now let's do restart, re-render. Yeah, there we go. Okay, and that's EX. And Actually, as you can see, in the short time that it took me to figure out what I did wrong, already the pulse is sort of halfway around. Let's look at the H field with the Y component, because that's better to look at, yeah. And this bend is looking pretty good. You don't really see any radiation. And let's test that though. One thing we could do here is I am going to specify the maximum value and then change that to have a normalization such that we'll see everything. Yeah, there's really almost no radiation. You can see this bend is working quite well there. There's just barely a little bit going out, but almost nothing. And we'll be able to wrap some actual numbers around that in just a moment. Where does this specify max value? Yes. All right, so this is going through here. Once this pulse goes through here, we'll be in a position to look at the transmission. Okay, so did I? Yeah, okay, I thought so. As I specified this to be PML, and you can adjust the connectivity and everything for silicon photonics anyway, and probably for free space. These are probably fine settings that have by default. Because PML, you can specify how many layers, what's the connectivity, what's the ramp function. But the defaults are just fine here. There will be on the order of 40 dB of back reflection, or negative 40, which is really pretty good, in my opinion, for a simulation. And so there's not a lot of field coming back off this boundary condition. Now, if we used more, you can use more with just a waveguide. And it actually does work. But then you're probably looking at 20 dB of back reflection. That might be enough to start to really distort your simulation. 40 dB is really good. And you can, in fact, see that. Let's see if I was even correct that it's around 40 dB, the render field. Yeah, okay, so before the max value was about 11, and now it's 0.1. So the field bouncing back has decreased in intensity by a factor of 100, and therefore in dB, it is down about 40 dB in power. So yeah, this is what we hope for. Now this reflected bit of pulse has gone through this surface. It will be further filtered because the inner product we use, as specified in the manual, will reject that reverse mode if we look for the forward mode. So let's go ahead and see what we have here. I am going to do a measurement. Okay, so the measurement was now done. And let's just take a look at what happened. So this is the field contents of operand 0, which I have now set to be the mode measure. Operand 1 is still set to the mode solve, so we see the mode solve. I'm just going to clear that so to avoid confusion. So now we're just looking at one thing, just operand 0. And by the way, you can save the file even while the FTTD thing is running. And what happens is it stores the information to connect to whatever server is running this FTTD. So if this were a remote machine or a cloud running FTTD, you could reconnect if you were disconnected. And so that's helpful if you have some monster simulation and you're in the airport and you lose your connection. The monster simulation will keep going and you can connect it and take your data later, maybe when you land or whatever. And so that was that's something you can kind of reattach and so on. Okay, but we don't need to worry about that right now. You can see a bunch of stuff. There's sort of the field that it downloaded if you want to look at the raw field. And then this is the thing that's really interesting. It's the forward modal amplitude of that was measured. And this is normalized, so c squared equals 1 implies 1 milliwatt of time averaged power. But again, that power normalization doesn't matter too much because we're just looking for a loss. Okay, so we see the frequency in hertz, very large, the optical frequency, of course. We see the complex modal amplitudes. And as we expected, there are 5 of them. One thing to look for, this is the real and imaginary part. One thing to look for, if you wanted to, you could save these right now. or you could just copy paste from here. This is the data that's the output of the simulation, basically. One thing to look for is that these, they're all fairly large, on the order of 1 to 10 in modulus, and they're all the similar modulus. What you don't want is where one of them is, modulus of 10, and then one is like 0.01. What that means is the pulse was probably too long, and so the frequency content was just in that one frequency, and then the other frequencies probably shouldn't be relied upon. How can we get a transmission? Well, there's a very easy way. We'll set this to operand 1 and here, and then we have an operation which is plot S21, and that simply divides the two coupling coefficients and takes 20 log 10 of the modulus. And the argument is not the most meaningful thing between these two different points. It's way more than 2 pi of radians, so just don't worry about the argument. But the actual S21, here we can see what the exact number is. Selected point 192.175 terahertz has an S21 of negative 0.0192 dB. So that's the actual bend loss that this simulation has measured, which is probably effectively 0. And you can see for the other points, it's similarly very low, negative 0.028 dB. That's a very small number. And that suggests that this bend is lossless to the extent that we can measure it. And is that 0.02 dB actually a real number? That is harder to say. It's such a small value that I wouldn't want to guarantee that this is a real number that we've measured from our simulation. The way I like to approach bends like this is to do a simulation of a series of varying bends where you can get the loss as a function of different bend radius, and then you can extrapolate. And so it might be that if we did that and we started at sort of 1 or 2 micron of bend where there's definitely going to be some loss, and then you extrapolated, you'd sort of see, yeah, exponentially, you probably want to extrapolate the log of the loss in dB, and you might see, hey, yeah, the loss is actually, if you extrapolate to this radius, it really is about this. And that is how I've always determined what the proper bend radius is for silicon photonics simulations, or not simulations, for design. And so I think that pretty much concludes the simulation. We have now measured the bend loss, and yeah, that's about it. So I'll leave it at that. Thank you for watching.